Hello, uh, good day, morning or afternoon. My name is Gabriel Adame Cabrera, and I am a graduate student in the master's program in Material Science and Engineering at the Autonomous University of Zacatecas. Today, I will present the development of a Python graphical interface for automating residual stresses in simulation in welding, using a Difflux subroutine and the Johnson-Cook model. Okay, starting with the introduction, it's worth mentioning that the thermomechanical welding simulations in software such as Abacus require the manual definition of numerous parameters, including geometry, mesh, boundary conditions, material properties, and the heat source subroutine. This manual process is time-consuming and prone to errors, especially for users without advanced simulation experience. Therefore, the need arose to develop a tool capable of automating and simplifying this workflow. Passing to the objective, the general objective of this work was to develop a Python graphical tool integrated with Abacus to automate the simulation of welding-induced residual stresses using Difflux and the Johnson-Cook model. These two models allows us to modify and predict some of these residual stresses in order to obtain what we need to simulate. The methodology of this progress was mainly developed in four main stages. First one, the users enters the welding operator um, parameters like voltage, current, and travel speed. These being critical operational parameters for the simulation welding process. Through the graphical interface shown here, which was developed using the automated Tkinter tool from Python, which is already uploaded to the software. So we just need to use it there. Second, the system automatically generates the geometry, mesh, and boundary conditions of the model. This is mainly doing, doing by a pipeline of 12 models distributed along the software. Third, the deflux subroutine is executed. This subroutine defines the heat input using Goldach's double ellipsoidal heat source model. At the same time, the thermomechanical analysis is performed in Abacus, where the Johnson-Cook model describes the material behavior considering strain hardening, strain rate, and temperature effects. Finally, the residual stresses results are obtained and visualized. As shown in the system architect diagram, the entire process is coordinated through a pipeline consisting of 12 modules with no manual intervention required from the user. Moving to the results, the system was evaluated using a single well bit on IC 308L stainless steel with temperature-dependent material properties. In the thermal analysis, 74 increments were completed successfully, representing a total simulated time of 57.5 seconds, 7.5 seconds of welding, and 50 seconds of cooling. The figure shows the resultant thermal field with temperatures reaching up to 3935 degrees Celsius according to the units defined in the model. In the mechanical analysis, 66 increments were completed. The resulting Von-Mises residual stresses were concentrated around the weld bit and the heat-affected zone. The maximum stress was approximately 178.1 megapascals. These are shown in both figure 3 and figure 4 of the entire analysis. It is worth mentioning that we are following a pipeline uh, simulation process where the user interferes directly with the graphic user interface, and then he just enters the variables that we need to model the parameters. Hit launch Abacus. The script runs Abacus instantly and allows to the software to just open itself with the parameters already loaded in Abacus, so the user doesn't need to upload manually, and this reduces the human error that could be interfering with the simulation. And he just hits the simulation button, and the software just starts and obtains a result. Regarding the automation, like I was saying, the setup time was reduced from several hours in the manual process to only a few minutes using the automated tool. Moving into the partial conclusions, because this is still a work in progress. The system was evaluated using a single well bit on IC38, like I said. But in conclusion, a tool was developed that integrates Python, Abacus, and Difflux into a single automatic workflow, making the simulation process more accessible to non-expert users. The incorporation of the Johnson-Cook model made it possible to approximately account for thermal softening and strain hardening under the simulated thermomechanical conditions. This contributed to predicting the residual stress distribution in the well bit and heat-affected zone. Finally, the thermal and mechanical simulations show stable numerical convergence. These results establish a numerical basis for future correlation and calibration with experimental temperature and residual stress measurements. All this is regarding the partial conclusions. Here I'll show my main references used for this presentation. This concludes my presentation. Thank you very much for your attention. I'll be happy to answer any questions or comments. Please leave them below and I'll be surely answering you as soon as I can. Thank you very much. This concludes my presentation. Thank you.